Good morning, everyone. My name is KaMan and come from R-CCS. Today, I would like to introduce our research topic. The title is the Introduction to a Data Assimilation-based Parameter Estimation Method and its application in the vector simulation. This project is start from the 2021, so that here I would like to try to explain some kinds of idea and the future plan. And as we know that to understand our real world, we need to set up a different model to describe their physical process. From a simple output-input model to a complex vector forecasting model. However, these kinds of model, they have two common problems should be solved. One is their imperfection, and the other one is the large of the parameterization in their physical scheme. So that in our team, one of our goal is try to find out a method to estimate these kinds of parameters automatically based on the data science. In the atmospheric model parameter, atmospheric model, there have many parameters in different physical scheme. For example, the cloud microphysics, turbulence, and the surface flux, and so on. And usually, we need to tune these kinds of parameter by hand in this scheme instead to improve the model, because we don't have any more time. However, previous study also used the data assimilation-based methods to estimate these kinds of volume. For example, the ensemble square root filter used in the no hydrostatic mesoscale model to estimate the eddy parameter. And for the global KaMan model, ensemble transport KaMan filter and the local ensemble transport KaMan filter is used in the parameter estimation. And here in our R-CCS, our team computational KaMan science research team and the data assimilation research team are cooperating to develop one vector, local vector model and data assimilation system. We use our regional meteorological model cross scale. This model is a surface library, can easily to simulate the climate and the vector forecasting. And in this library, including the processing, simulation, post-processing, and analyze. And for the parameter estimation, we've used the ensemble transport KaMan filter in this system. To testing this system, we did some experience. For example, we assume this vector model is a perfect model and create a 2D scoreline experience. We try to find out rainfall speed coefficient in a cloud microphysics scheme, just like this formula shows that the CL, our target parameter, is a key parameter for cloud organization. And this figure shows the simulation of the radar refractivity for the scori. First, we assume we identify the true volume as a default volume of the CR, and then at the beginning we random the initial volume in the wrong region with different standard deviation. After a few data assimilation cycle, we can see that the wrong initial volume can vary to congruent to the true volume with different standard deviation condition. And this ideal experience shows that the smaller standard deviation, the better estimation precision. And the higher standard definition, the faster the confidence speed. So that let us look at the real world. In the real world, we select a typhoon case in the June 2004 around the East Pacific Ocean. And our physical scheme target is a cumulus scheme, and we select the release rate of cap in this scheme. And this figure shows that the simulate precipitation without data assimilation, with the data assimilation, and with data assimilation and parameter estimation. Finally, we can see that during a few data assimilation cycle, we can see that the simulation result with data assimilation and the parameter estimation is very close to the observation. However, let's move to the time series of the parameter estimation of this parameter. We cannot see the confidence during these 10 days. So that there have one questions. It is so that in our field world, should we try to find a constant true volume with time, or try to find a less smaller error for our target phenomenon? And not only the precipitation, we try to use this system to other phenomena. For example, the dust emission, dust simulation. We select a dust simulation in May 2015 in the East Asian Gobi Desert. And our target physics scheme is a dust scheme. This scheme is a relationship between the wind speed and the land surface condition. These kinds of land surface condition are parameterized. For example, the soil texture, soil moisture, and the vegetation. Here, in our experience, we try to estimate the parameter of the ideal threshold wind speed, because these are key parameters of the soil texture affect on the dust emission. Because this parameter is default volume in many dust schemes, this default volume is calculated by the global average. And also previous studies shows that this kind of global average volume cannot reproduce the dust frequency in the East Asia. And we can also see that if we try to tune this parameter to the observation level, they have a good agreement in the dust inference frequency in the Gobi Desert. And this study is go forward now. And I would like to summarize this presentation. Our vector data assimilation system developed by our team, and we test this system under different target case. One is the perfect model ideal case, and the other one is the real imperfect model case. And in our next step, we try to establish the RIKEN-based parameter estimation for consider these kinds of parameter, how spatially distribution change. And we also compare these two cases. We can see that data assimilation is very good for the initial condition error to test and validate. But in the real world, we need to more consider the model error, so that I under the project of the protection for science, and in this project we try to collaborate with different science team and try to find out not only the data assimilation methods, but also try to using the machine learning to find out these kinds of parameterization problems. Yes, thank you for listening.